Hello everyone, welcome to DP Tutorials by Donny Jerwa. In this teaching module and teaching lesson, we will emphasize and elucidate on another important application of Ampere's circuital law, which is to find the magnetic field due to a long straight solenoid. Now, what we have learned from Ampere's circuital law is that it states that the line integral of the magnetic field, on any closed curve is equal to mu naught times the current enclosed by that circular loop. Okay. So this is the statement of Ampere's circuital law. So from here, what is this solenoid? When you look at this picture, if we have a long wire and if we wrap this wire along a cylindrical metal, that means this type of arrangement is what is known as a solenoid. So a long coil which is wound on a cylindrical material having many turns per unit length, and all these turns are very close. Here all those turns are very close to each other, or you having closely spaced loops. So that type of material is known as a solenoid. So when we pass current across a solenoid, keep in mind that this solenoid also stores energy in the form of magnetic field, and that particular material is what is known as an inductor. So we will describe about this in the later section, and we have come across these devices or electrical appliances at home where we use as induction cooker or induction based cookers. Okay, all these are nothing but foundation or application of an inductor or what is known as your solenoid. So from here we have this solenoid, and when we pass current on a solenoid, that means it generates magnetic field. So from here, if I pass current on the solenoid, so like for example over here, if I pass current on the solenoid, I am passing current on the solenoid. This is the direction in which the current I is moving, and from here the current I is coming out. So this particular end of the conductor, all these spheres which I have drawn over here, all these are nothing but what? All these are nothing but magnetic field. Okay, these are nothing but what? These are nothing but magnetic field or magnetic field lines. Okay, these are your magnetic field lines, and the magnetic field lines generated by a solenoid are similar to the ones generated by a bar magnet. If I have a bar magnet, this is a permanent magnet in which one end of the magnet is the north pole. Okay, in which one end of the magnet is the north pole and the other is the south pole. Like for instance, if I consider this is the south pole and if I consider this is the north pole, we know that there will be magnetic field lines generated by this magnet. So from here I will draw these field lines. These are the magnetic field lines generated by the magnet. This is also the magnetic field lines generated by the magnet. There will be many field lines, okay, generated by this bar magnet, and from here you will find out that the direction of the magnetic field lines, it is always pointing from the north pole of the magnet. Outside the magnet, it is pointing from the north pole, it goes to the south pole. Emanating from the north pole, it goes to the south pole. Emanating from the north pole, it goes to the south pole. Whereas inside this magnet, okay, inside the magnet, it comes out in this direction. Okay, whereas inside the magnet, it comes out in this direction. So from here, these are the field lines. These are the field lines. Outside the magnet, it starts from north, it goes to south, whereas inside the magnet, the magnetic field lines, okay, moves from south, it goes to north. It moves from the south and it goes to the north. It moves from south, it goes to north. It moves from south, it goes to north. So from here also, when you look at this way in which the current is entering across a solenoid, okay, and if these are the direction of our field line. So this particular end where the current, this particular end of the solenoid where the current enters, that will behave as what? This will behave as the south pole. Okay, that will behave as the south pole. And this particular end of the solenoid where the current leaves, this will behave as what? This will behave as the north pole. So that is why when you look at all these curves over here, all these magnetic field lines will be in this direction. All these magnetic field lines will be on this direction. So all these, even from here also, all the magnetic field lines will be on this direction, and it will goes inside. Whereas the magnetic field line inside the solenoid will be straight lines, and it will be directed from south to what? From south to north. So from here it is very obvious that when you pass current on a solenoid, okay, when you pass current I on a solenoid, it will generate magnetic field, and the magnetic field generated by the solenoid are represented by these magnetic field lines, and it is similar to the magnetic field lines generated by what? Generated by a bar magnet. Okay, generated by a bar magnet, which convinces us that if we have current, it generates magnetic field. So this is what is known as the magnetic effects of electric current. Now from here, let us consider. Okay, let us move on into the derivation. Let us consider this current carrying this solenoid, and all these solenoids will be having many turns. So let the solenoid have n turns per unit length. And suppose from here on this solenoid, in order to pass current, you should have what? You should have a battery. So from here, this is the positive terminal of the battery, this is the negative terminal of the battery. We will put a one-way key. Okay, we will put a one-way key, and once we insert the plug, okay, once we insert the plug across this one-way key, okay, once we insert the plug across this one-way key, we know that current will flow. Okay, current will flow across that circuit. And when current flows across the circuit, always current flows from the positive, it goes to the negative. So from here, let current I, and it will move across this point. Okay, so this is the particular point where the current enters. So when you consider this loop, okay, when you consider this loop, this is the current at this particular loop. Suppose this is the point where the current enters. So at this particular point, it goes into the loop. So that is why the magnetic field, okay, the magnetic field will be represented by cross. It moves, it goes, and then from here it comes out. Okay, it comes out from this particular point. So since it comes out from this particular point, the direction of the current will be represented by dot. So from here again, see, this is the direction the current flow. It moves inside, and from here again it moves. The current is moving from here. It goes into the solenoid. From here, the current goes inside. So it is represented by cross, and from here it comes out. Okay, from here it comes out. So it will be represented by dot. Similarly, from here also, the current. See, the current is moving like this, and this will be the direction. That arrow indicates the direction of the current, and then from here it comes out. It goes inside, represented by cross, and then it comes out, represented by that dot. Again, from here the current moves. Okay, it moves like this, and then the current from here it comes out in this direction. Okay, and then the current from here it moves out and comes out in this direction. So all these will be the direction in which the current is moving. Okay, it moves in this direction, and similarly for all the different one, for all the different curves. Okay, for all the different turns. Okay, so from here it is obvious that from here, see, it enters. This is the direction of current flow to this particular turn of the solenoid. So it it enters. Okay, it enters, or it goes inside. Okay, and from here, from this particular point, it will comes out. So I will represent by what? Dot. So all these points where the current, okay, where this current goes inside, this will be represented by what? The current that enters that point will be represented by cross, and from here, since it moves out, okay, it comes out, so it will be represented by dot. So those are what? So those are some of the important points that you need to remember. Then from here, since this is the direction in which the current is moving inside the solenoid, So there will be magnetic field lines associated within. Okay, there will be magnetic field lines in this form, magnetic field lines. So there will be magnetic field lines in this form. So there will be magnetic field lines emitted by the solenoid. So all these magnetic field lines will be emitted by the solenoid. So those are what? Those are your magnetic field lines. So since the current enters this end of the solenoid, so this end of the solenoid will behave as the south pole, whereas this end of the solenoid will behave as what? Will behave as the north pole. So the magnetic field lines will always move from what? From this direction. Inside the solenoid, it will move from south to north. It will move from south to north. Whereas outside the solenoid, it will move from north to south. Okay, from north to south. So those are some of the important things that we need to remember. So from here, let I be the current passing through the solenoid. This is the current I which passes through the solenoid, and it produces magnetic field. Okay, similar to the magnetic field produced by what? Produced by this bar magnet. Okay, and in order to determine the magnetic field due to this solenoid, we have to construct what? We have to construct an Amperian loop. But this Amperian loop taken over here is not a circular, but it will be a rectangular. So that rectangular loop will be in such a way that it encloses, okay, it encloses the solenoid inside. So it also passes through the axis of the cylindrical solenoid. So over here, this dotted line which I have drawn, this is nothing but the axis of the solenoid. So here comes the important step that it requires your attention. So from here, let us take this rectangular Amperian loop. So I will draw a rectangular Amperian loop. So from here, it means like this. That means I have to draw a rectangular Amperian loop, and this rectangular Amperian loop which cuts through the solenoid. Okay, so over here I will take this rectangular Amperian loop, and taking this rectangular Amperian loop, I will place this rectangular Amperian loop in such a way that it passes or cuts through the surface. Okay, it passes or cuts through the surface. So from here, this is our Amperian loop, and this Amperian loop will be in such a way that this one end of the Amperian loop, it passes along the axis. Okay, it passes along the axis of the solenoid. And keep in mind, okay, keep in mind that the direction of this, the direction of your magnetic field, the direction of your magnetic field is in this direction. Let me indicate by this by this yellow color. This will be the direction of what? This will be the direction of your magnetic field. Okay, that will be the direction of your magnetic field. So this will be the direction of B. Okay, that will be the direction of your magnetic field. So this will be the direction of your magnetic field. Why? Because this end, the current, that end of the solenoid where the current enters, that will behave as the south pole. So this will behave as the south pole, whereas this end of the solenoid, this will behave as what? This will behave as the south pole, and this will behave as the north pole. So from here, this will be the direction of magnetic field lines inside the solenoid. Now we have taken this rectangular. Okay, I have taken this rectangular Amperian loop, and I will construct this Amperian rectangular loop in such a way that I will place this rectangular Amperian loop such that it passes, okay, the one length of the Amperian loop passes through what? Passes to the axis of the solenoid. So from here, let me take this as point. Okay, let me take this Amperian loop. Okay, Amperian loop as point P, Q, R, and S. Okay, P, Q, R, and S. So this is our rectangular loop. Okay, this is our rectangular loop. So this is P, Q, R, and S. This is our rectangular Amperian loop. Okay, this is our rectangular Amperian loop. Now from here, also, if this PQRS, okay, this will be the length of that rectangular loop. Okay, even from here, I can see that this is our rectangular Amperian loop. Okay, P, Q, R, and S. This will be the length of the rectangular loop. This will be the breadth of that rectangular loop. Say, like for instance, this is the direction of B, if I consider, okay, if I consider that this, okay, if I consider any element, so from here also, if I consider any element, or if I consider from here also any element, this is the element dl of small portion of PQ dl. So from here, if this is the direction of dl, that means from here I can consider the what, the element vector. So taking this yellow colored vector, let this yellow colored vector represent the element, the current the element, okay, the element vector of that dl bar. So this will be what? This will be the element vector dl bar. So this is our element vector dl bar constructed at that particular point. So this is your element, okay, element vector dl bar. Similarly, the magnetic field along this length PQ, okay. Similarly, the magnetic field along that length PQ, or from here, if this is dl, I will take this yellow colored vector, and this yellow colored vector will represent our what? This yellow colored vector will represent our dl bar. And from here, since we know that the direction of the magnetic field, is along the same direction, the direction of the magnetic field is pointing on this direction. This is the direction of the magnetic field. This is the direction of the magnetic field from here. Then represented by this pink colored vector, we will take this. This will represent what? This will represent our magnetic field vector. So this will be what? This will be our magnetic field vector. So this will be what? This will be that pink colored vector will represent our what? Our magnetic field vector. Similarly, over here in another diagram, we will take this pink colored vector. This pink colored vector will represent what? Will represent our magnetic field vector. Okay, our magnetic field vector. Similarly, over here along this arm, okay, along this arm QR and along this arm PS, also we can construct, okay, we can consider another element. Even on this arm PS also we can consider another element. Let this element be dl, and let that element also will be dl. Similarly, over here also we have to represent the element vector. So I will take this yellow colored vector, and this yellow colored vector will represent what? Will represent our element. That will be our element vector dl bar. And along this arm PS, we will take another element. Let this element be what? Be represented by this yellow colored vector, and this will be placed over here. Yeah, this will be placed over here. That will be what? That will be our current our element vector dl bar. Similarly, over here, using the same concept, at this particular point, we can consider this as the element. Okay, this as the element. So let that be the let this be the element dl. So, and over here along this arm PS also, let dl, okay, let dl be the element. So by in terms of the vector, that means in terms of the vector, we will represent this by this yellow colored vector, and this yellow colored vector will represent what? Our dl bar along the along this direction. Along this arm PS also we will take another vector. This vector will represent what? This vector will represent our dl bar vector. But when you look from this figure, it is very obvious that since this is the direction of our magnetic field, on the arm PQ, the direction of B and the direction of B, okay, the direction of B and the direction of dl are in the same direction. B and dl are in the same direction. Okay, B and dl are in the same direction along the arm PQ, which means that over here theta will be equal to how much? In this case, theta will be equal to 0 degree. But when you look with respect to arm QR and with respect to this arm PS, this is the direction of B, the magnetic field. Okay, so the direction of our magnetic field in this case, okay, the direction of our magnetic field in this case will be in this direction. This is the direction of B. Okay, this will be the direction of B, which means that the angle between this dl, the angle between this dl bar of this element and this b are what? Are 90 degree with respect to each other, even for this element, even for this element. This is the taken direction of b. This is the taken direction of b. So at this particular point, that means this will be the direction of what? This will be the direction of b. And from here also it is obvious that the angle between dl bar, this angle between this vector dl bar and this b are what? Are 90 degree with respect to what? Are 90 degree with respect to each other. So from here it is very pertinent. Okay, it is very pertinent that the direction of b and dl should be taken very carefully. Okay, it should be taken very carefully. From here, let us reiterate that the direction, this will be the direction of, this will be the direction of b. So in this case, it will be 90 degree. Similarly, over here also, this will be the direction of 1. This will be the direction of b. So this angle over here will be 90 degree. Whereas in this case, the angle is how much? The angle is 0 degree. Why? Because they are in the same direction. So from here, when you look with respect to arm RS, this is the arm which is outside. Okay, this is the arm which is outside the solenoid. This arm RS is outside the solenoid. This arm RS is outside the solenoid. So the magnetic field will be negligibly very small. Okay, will be negligibly very small. So those are the important things that we need to that needs attention, okay, with regards to construction of Amperean loop. Okay, construction of Amperean loop. So from here, we will have to apply Ampere's circuital law. Okay, Ampere's circuital law. So from here, this is the definition of mathematical expression of Ampere's circuital law. Then from here, the line integral, applying Ampere's circuital law to this loop, okay, to that closed path PQRS, we have line integration of b, okay, line integration of b dot dl, okay, line integration of b dot dl will be equal to mu naught, okay, mu naught I, okay, mu naught I. But over here, since there are n turns, okay, since there are n turns of the coil, so we will write n l I, okay, n l I. Why we write, what is this L? This L is nothing but the length of the solenoid. That L be the length of the solenoid. This is the length of the solenoid. So capital L, okay, not small l, it will be capital L. Let capital L be the length of the solenoid. So if you multiply the length of the solenoid with all those number of turns, okay, with all these number of turns, that will give you the total contribution of the magnetic field. Okay, total contribution of the magnetic field. So from here, let us mark this as equation number 1. So if you want to find the magnetic field due to that solenoid, that means you have to focus. Okay, you have to focus with respect to this Amperean loop. So now the right hand side, okay, the right hand side of that equation 1, the right hand side of that equation 1 can be rewritten. Okay, can be rewritten. That means you have to consider the contribution to the arm PQ, the contribution due to the arm QR, the contribution due to the arm RS, and the contribution due to the arm PS, okay, or SP. So from here we will write down, okay, integration, okay, integration of b dot dl, integration of b dot dl, integration of b dot dl, the integration of b dot dl will be integration due to what? Due to this arm PQ, from P to Q of b dot dl, okay, b dot dl, integration of P to Q of 1, b dot dl, b dot dl. plus integration from Q to R of B dot dl. Then integration, okay, closed integration or line integral of the integral from the upper part R to S, okay, R to S of B dot dl, B dot dl, plus integration, okay, integration or close integration from this integral, okay, from that integral, close integration of from P to S of B dot dl, okay, B dot dl. So this I can mark this as relation number 2. So from all these four contribution, you have to find the magnetic field. So from here it is obvious that the magnetic field due to those all contributions should be found out. But from here, this arm PQ, okay, from that arm PQ, from this figure 2, if I name this as figure 1, if I name this as what? As the figure 2, if I name this as the figure 2, the second figure. So when you look at this figure 2, that means for that part PQ, for this part PQ, which is inside, okay, that part PQ is inside the solenoid. This part PQ is inside the solenoid. So along the axis, okay, along the axis, the magnetic field vector B, okay, the magnetic field vector B and that dl bar are in the same direction. So from here, this direction of magnetic field B, okay, given by this yellow mark, and the direction of dl are in what? Are in the same direction. So which means that the angle between them is 0, and also they are parallel to each other. So inside the solenoid, the magnetic field vector, and the magnetic field vector B bar and our element dl bar, okay, and our dl bar, they act in what? They act in the same direction. They act in the same direction. And when they act in the same direction, the angle between them is what? The angle between them is 0 degree. Okay? The angle between them is 0 degree, which means that integral, okay, which means that this integral from P to Q, that is the line integral from P to Q, that line integral from P to Q of B dot dl will be equal to what? Line integral from P to Q. Yeah, you have to use the concept of dot product B dl cos, okay, B dl cos of 0 degree, okay, B dl cos of 0 degree, but cos of 0 degree is equal to 1. So we have only integration from P to Q B dl, okay, P to Q B dl. And from here, if you look with respect to this diagram, the contribution from the arm, okay, from the arm QR, and from the arm SP or PS, the element, okay, the magnetic field, okay, the magnetic field and the element are what? Are perpendicular to each other. Okay, the magnetic field along this part, that means this is the magnetic field along this part QR, and the magnetic field along what? Along the arm PS. This is the direction of the magnetic field along arm PS. This is the direction of the magnetic field along what? Along QR. So which means that B and dl are perpendicular. B and this dl bar are also perpendicular, both with respect to SP and both with respect to QR. Okay, so from here, which means that the angle between them is how much? The angle between them is, okay, is theta equal to what? Theta equal to 90 degree. Okay? Theta equal to 90 degree. So from here it is very obvious that these integrals, okay, this integral QR and PS. So this is the integral from Q to R, this integral, and from this integral p to s, okay, all these two integrals will contribute to 0. So from here let us find out and verify that, which means that the integration from q to r of b dot dl is the same as the integration from p to s of b and dl. So from here this will be integration. I can write only a common integral, okay, a common integral. So from here this will be b dl using the dot product. So from here it will be 1. We have to remove that bar sign. That means over here this will be cos of 90 degree, but cos of 90 degree will be equal to 1. Cos of 90 degree will be equal to 0. So from here both these two integrals will be equal to 1, will be equal to 0, which means that there will be no magnetic field along the arm QR and along the arm PS. So which means that over there will be no contribution along those arms QR and SP, even from that arm, okay, even from this arm RS, okay, even from this arm RS or SR. Since this arm is outside the solenoid, okay, since that arm is outside the solenoid, the magnetic field, okay, the magnetic field is very strong for regions, okay, the magnetic field is very strong for regions inside the loop or inside the magnetic field is very strong for regions inside what? Inside the solenoid. So these are what? These are the magnetic field lines. These are the direction of the magnetic field lines. But for regions outside, okay, but for regions outside the magnetic field lines, that means if for this arm of that Amperean loop, SR will be very small or negligibly small. So which means that over there in physics we can neglect that part. So the magnetic field for the arm RS, okay, from here the magnetic field for the arm RS, since it is outside the solenoid, it is very small and it is negligible, so it will be 0, which means that is, okay, that is the integration for that arm R to S, okay, then from R to S, okay, this B dot dl, this will be equal to 1, this will be equal to 0, okay, that will be equal to 0. So next from here, what do we have to do is that we have to find the net contribution, okay, the net contribution due to this equation 2. So from equation 2 it is clear, okay, from equation 2 it is clear, therefore equation 2 implies, okay, therefore equation 2 implies the line integral of B and dl, the line integration of B and dl, that means you have only the contribution from that P and Q, okay, only from the contribution from P and Q. This will be B dot dl bar. Then the rest of those arms, okay, the rest of those arms will be equal to 1, will be equal to 0. So this will be B bar dl bar plus all those contribution from those arms will be 1, from the arm, okay, QR, from the arm QR, from the arm PS, and from the arm RS, all those will be equal to 1, 0, 0 and 0. So from here also we have found out that this will be equal to 1, line integration of B dl. After derivation, this will be equal to B and dl. If you look from here, this will be integration of P to Q. Integration from P to Q, B dot dl will be equal to line integral of B dot dl. Okay, line integral of B dot dl. Then we know that integration, since the magnetic field, okay, since the magnetic field B is constant, since the magnetic field B is constant, since this magnetic field B is constant, so we can take outside of the integration sign, okay, outside of the integration sign, so B is taken outside, we are left with integration over dl, okay, integration over dl. But when you look from that figure, okay, when you look from this figure, that means if I consider all those small elements dl, that means that will be equal to 1. If I consider all those small dl, that will be equal to 1. That will be equal, if I consider all these small elements over here, dl, that will be equal to the total length of the solenoid. Okay, that will be equal to the total length of the solenoid. So from here, it implies that this integration over dl also, integration over dl, this will be equal to capital L, and this capital L will be the whole length of the solenoid, length of the solenoid, length of the solenoid. So from here, this will be equal to 1, dl. Then what is this integration of b dot dl? If you look from equation 1, b dot dl, okay, will be mu naught nli, okay, mu naught nli. So from there, you just write over there, this will be equal to mu naught n l and I. So this is by using 1. This is by using that equation 1, because we have applied Ampere's circuital law, which means that over here, this b, we can cancel l and l, which means that b will be equal to what? Mu naught, okay, mu naught ni, mu naught ni, which means that over here, this magnetic field b is purely dependent upon the number of turns. More is the number of turns, more will be the magnetic field of the solenoid. Less is the number of turns, less will be the magnetic field line. So this is one of the most important concepts. That means if you look from that diagram, if we have more number of turns, when the number of turns of the solenoid is more, that means the strength of the magnetic field also is more, because the formula for the magnetic field due to the solenoid is B equal mu naught Ni. Say, like for instance, you have inside that inside this solenoid also we can keep a material, okay, inside this solenoid, okay, inside over here, we can keep a material, okay, we can keep a material of suppose such as soft iron, okay, we can keep a material which is made of soft iron. This material, soft iron, is a it is a ferromagnetic substance. It is a ferromagnetic substance. It increases the rate of storing magnetic field, or increases the magnetic properties of the substance. And if that soft iron core is having a permeability, okay, is having a permeability mu r, then with respect to the absolute permittivity or absolute permeability of free space, that means the magnetic field B, it gets modified if you place that material having a relative permeability mu r. So over here, if mu r, if mu r be the relative permeability, okay, if mu r be the relative, if mu r be the relative permeability of the material inside the solenoid, then the magnetic field due to the solenoid is given by what? Is given by this expression. Okay? Therefore, that means this B, we just multiply mu r on the above equation, mu naught, mu r, Ni. So this will be what? This will be the equation. Okay? This will be the equation for the magnetic field due to the solenoid when a material having relative permeability mu r is placed inside it. Okay, is placed inside it. So from here, some of the important conclusions. Okay, B is dependent upon N. More is the number of turns, more will be the strength of the magnetic field. So B depends upon the number of turns and also the current I. So there are two things that we can draw. Number one, B is proportional to N, and number two, this B, it is also directly proportional to the current I. So more is the current, more will be the strength of the magnetic field. So these are the two conclusions which we draw from this equation. So B is stronger inside the solenoid and weaker for regions outside it. I have explained about that. B is stronger for regions inside the solenoid and weaker for regions outside it. And from here we will discuss the nature of what? The nature of the magnetic field due to a solenoid. So we know that when we pass current across a solenoid, okay, when we pass current across a solenoid, this will be the positive terminal, this will be the negative terminal, and from here, this is the key, okay, this is the key. When we insert the plug, current I will be passing, okay, the current is moving in this direction, okay, the current is moving in that direction, and from here the current, it enters this point. So this is the point where the current enters, so it will be marked by cross. This is the point where the current enters, it will be marked by cross, and from here it enters inside or goes inside. This is the point where the current goes. This is the point, this is the particular point where the current comes out. Again, comes out. So at this particular point, we will represent by what? We will represent by dot. Okay, at this particular point, we will represent by dot. So I have told you that this end, where this particular end, the current is entering this end of the solenoid. So that end, that end of the solenoid where the current I is entering, that end of the solenoid will behave as what? That end of the solenoid will behave as south pole. Okay, this will behave as the south pole, and this end of the solenoid, the other end of the solenoid, will behave as north pole. So there will be magnetic field lines. Okay, there will be magnetic field lines. So I will take some of the magnetic field lines, representation of the magnetic field lines. Okay, these are the direction of the magnetic field lines. So from here, these are the direction of the magnetic field lines. Okay, these are the direction of the magnetic field lines, and also these are the direction of the magnetic field lines. Okay, magnetic field lines. This is also the direction of the magnetic field lines, and also this is the direction of the magnetic field lines. Okay, these are the direction of the magnetic field lines. These are the direction of the magnetic field lines. So from here, in this case, all these magnetic field lines, okay, all these magnetic field lines for regions inside, it goes from south pole, then it goes to north pole. For regions inside, okay, this is inside, and this is outside the solenoid. For regions inside, the magnetic field lines, it starts from south and it goes to north along the direction of flow of current. Okay, so this will be the direction of movement. This will be the direction of movement of magnetic field lines. Whereas for regions outside, if I complete this, that means it will start from north and it goes to south. And for regions outside, if I complete this magnetic field line, that means it starts from north and it goes to south. It starts from north and it goes to south. Inside, it goes from south and it goes to north. Then similarly, okay, over here, if I want to represent it more clearly, we know that this is the particular part where the current enters. Okay, so this is the particular part where the current enters. So making use of the right hand thumb rule, okay, that means from here, since the current is entering this point, so it will be marked by what? It will be marked by the cross. So there will be magnetic field lines across this point since the current is entering from here. So which means that this is the point where the current enters. So from there, when you look precisely, you will find out that that is the particular point where the current enters. And from this particular point, the current leaves, or it comes out. So from there, okay, So from there, making use of those analogy, we can represent them in another form. Okay? So from here, if we take this, now let us try to represent this. Okay, this will be the point where the current enters, okay, or goes. Okay, I've written over here goes. This will be the point where the current goes, and this will be the point. So this will be the point where the current goes, and from there, that means all these will be the point where the current goes inside. So that is why I will represent by what? I will represent that by a cross mark. I will represent this by a cross mark. Okay, I will represent that by a cross mark. Okay, cross mark. So these are regions where the current goes inside the solenoid, represented by cross mark. Okay, represented by cross mark. So if you use the right hand thumb rule, okay, if you use the right hand thumb rule, that means this is the thumb and this is the curl of the fingers, this is the direction of the current. So from here, when you apply your right hand thumb rule, so all those circular spheres, okay, all these circular spheres will represent the direction of your current element. So from here, since it is moving, so all these will be moving in one. All these loops will be moving in the counterclockwise direction. Over here also these loops, these pink colored circular loops, all these will be representing the magnetic field. Okay? Magnetic field. Okay? From here moving in this direction. Magnetic field. Okay? Magnetic field. So all these will be moving in the what will be the direction of these circular loops? So these directions of those circular loops, since it is cross, so it will be what? It will be in the anti-clockwise direction, or the point where the current goes, okay, goes inside. So this will be the direction where the current goes inside. So from there, which means that if you look from this sphere, if you look from that sphere, that means that analogy, that means from here all this magnetic field line is moving on this direction. Even from here also, all the magnetic field line are moving on direction. They are also moving on this direction from south end of one end of the solenoid behaving as south pole, and to the other end of the solenoid behaving as the north pole. So from here, that means if I take the total effect of all these spheres, that means I can represent by what? I can represent by this vector. So from here, making use of this, that means I can place it over there. Okay, that will give us, okay, this will give us what? Direction of what? Movement of current. So from here it indicates that the direction of movement of magnetic field is always from south pole, it goes to north pole, and for regions outside it will be always from south to north, okay, south to north. Even for this lower region, if you look for the lower regions, which means that I'm talking about these points, see the current is moving, it goes and then comes out for this point. Then the region, that this particular point it goes, then from here it comes out. Okay, so all these points from here, these will be the points where the current comes out. This will be the point where the current comes out. So it will be represented by dot. Okay, so over here also this will be the point where it comes out. So it will be represented by dot. Okay, so similarly in that way, we will represent these spheres. Okay, these spheres. So from there, this also will be the direction of the current where it comes out. Okay, this will be the point where it comes out. This will be also the direction where it comes out. And from there, okay, that means since this is the point where the current comes out, so we have to represent this by what? By dot. This is also it comes out, therefore we have to represent it by what? Dot. Dot and dot. Since it is coming out, when you use your right hand thumb rule, so when you use your right hand thumb rule in that case, so when you use your right hand thumb rule in that case, since the current from the lower part, it is coming out, so this will be what? This will be in the clockwise direction. So since it is coming out, so it will be in the clockwise direction. That will be your direction. Even for this also, that will be in that direction. That will be in this direction, clockwise direction. Okay? Clockwise direction. It will come from here. This will be the direction. 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 If you take into the total effect, so from the lower part, the current is coming out represented by dot. So all these will be your sphere. If you use your right hand thumb rule, okay, you use your right hand thumb rule, thumb in pointing out the current, so you'll find out that the current will be in what? The current will be in the clockwise direction. Your current will be in the clockwise direction. The current will be in the clockwise direction. So from here, if the current comes out of the solenoid, so the direction of your magnetic field will be in the clockwise direction. Okay, it will be in the clockwise direction. So from here, I will take this and then place over here. Then when you place over there, with respect to all these direction of your magnetic field, okay, magnetic field, that means since these are pointing in this direction, so it will be on that direction. Since this is also pointing in that direction, so it will point on that direction. And from here, this is pointing on this direction, so which means that this will be pointing on that direction. So which means over here that the direction of the magnetic field lines, okay, always it begins in this direction. Okay? It begins in that direction. So inside the solenoid, outside the solenoid, it moves from one. So it moves from the north pole. It moves from the north pole. It goes where? To the south pole. See, this is the direction. From here also, it moves from the north pole. These are the direction. Okay, these are the direction. And it comes from the north pole and it goes to the south pole for region outside. And for region inside, it goes from the south pole and it goes to the north pole. Similar to the magnetic field lines generated by what? Generated by the bar magnet. So if you look over here, this is the direction of the magnetic field. This is the direction of the magnetic field. This is the direction of the magnetic field outside. This is the direction of the magnetic field outside. These are the direction of the magnetic field inside. This is also the direction. This is also the direction of the magnetic field line inside. This is the direction of the magnetic field line inside. Okay, this is the direction of the magnetic field line inside. So these are some of the important points that we need to know. So from here, keep in mind that the end where the current enters will behave as south pole, and that opposite face will behave as the north pole. Okay, so magnetic field line inside the solenoid are what? Are uniform and are nearly parallel to each other. So all the field lines, see, if you look from here also, the field lines, this is the field line number 1, this is the field line number 2, this is the field line number 3, and this is the field line number 4. If you look with these field lines 1, 2, 3, and 4 inside the solenoid, okay, for regions inside the solenoid, they are what? They are parallel to each other. So the upper part of the solenoid, this upper part of the solenoid are represented by cross mark, and the lower part of the solenoid are represented by what? Are represented by dot. Okay, the lower part of the solenoid are represented by what? Are represented by dot. So the upper part indicates, okay, the upper part indicates that it is the part of the current where it what, where it enters or it goes, and the part of the solenoid, or part of the current where the part of the solenoid where the current uh, comes out, it will be represented by what? It will be represented by dot. So the magnetic field is similar to that produced. This is also very important. Yeah? The magnetic field produced by a solenoid is similar to that produced by a bar magnet, and the magnetic field always starts from north to south. Okay, it always starts from north. Okay, it goes to south for regions outside, both for this solenoid and both for the bar magnet. And for regions inside, it moves from north, it goes to south, it moves from north, it goes to south. From here it is entering, it is entering, it is entering. Okay, and for regions inside, it moves from south and it goes to north. It goes from south and it moves to north. So these are what? These are the direction of the bar magnet. This is the magnetic field line of the, what is this? This is your bar magnet. What is this? This is your solenoid. Okay, this is your solenoid. And for a solenoid, okay, and for a solenoid, that means from here, when you look, that means when you look for this particular discussion, it is very important that we have to pay more attention. Okay, pay more attention. Then from here, okay, from here we will try to represent these will be what? These will be the direction of the magnetic field lines due to a bar magnet, similar to what is being produced by this solenoid. Okay, so magnetic field lines will be the same. Okay, the magnetic field lines will be the same. So from here, the current enters at this point, the current enters on that point, the current enters on that point. So from here, this end of the solenoid will behave as the south pole, this end of the solenoid will behave as the north pole. Okay, similar. Okay, but over here, this is a permanent magnet. This is the permanent magnet. Okay, whereas over here, this solenoid will behave as what? This will behave as a temporary magnet. Okay? Temporary magnet by passing what? By passing current I. So you can produce magnetic field. So the direction of the magnetic field inside the solenoid will be from south to north, and for regions outside it, it will be from north to south. Okay? For regions outside it will be from what? From north to south. Okay? North to south. So that is some of the most important things that we need to understand. Then the intensity of the magnetic field. Okay, the intensity of the magnetic field due to the solenoid can be increased by increasing the current I and the number of turns, since B is proportional to N and also B is proportional to I. Then from here, the upper part will be the current where it goes inside, and the lower part is represented by the cross mark. Okay, all those circular magnetic fields are in the clockwise direction governed by right hand thumb rule. Then from here also we can represent, say, the magnetic field line due to a solenoid. On the lower part is represented by what? By the dot. Okay, it is represented by dot. And from here, that means on the lower part, the circular magnetic field lines are in what? In the clockwise direction. Only in the upper part, that means this will be in the in the clockwise direction. I mean, in the clockwise direction, whereas in the lower part, this will be what? In the anti-clockwise direction. Then from there, I have explained to you why we keep a soft iron core. Okay, why we keep a soft iron core. The magnetic field of a solenoid can be enhanced by keeping a material known as a soft iron core. Okay, and these soft iron core act as what? Magnetic core, behaving as what? Behaving as an electromagnet, which creates stronger and denser magnetic field. Okay, when current passes through it, thus behaving as what? Thus behaving as a temporary magnet. So this soft iron core is also known as a ferromagnetic materials, and these ferromagnetic materials can be magnetized. See, from here also I can get magnetism once there is current. When you look from that relation B equal mu naught and I, okay, if I is 0, it means that B also will be 0. So which means that so long as you pass current on the solenoid, there will be magnetic field. If you don't pass current on the solenoid, there will be no magnetic field, which clearly explains this concept. That means they can be easily magnetized when current passes through the solenoid, and it gets demagnetized when current is removed. So when you remove the current, or when current is 0, then B also will be 0. In other words, soft iron core uses inside a solenoid because soft iron core are used inside solenoid because it does not what? It does not retain its magnetism when current is switched off. That means it does not become permanently magnetized. So you'll be learning about two types of magnetic substances, which are known as ferromagnetic substance, and another magnetic substance is also known as what? Paramagnetic substance. Okay? Paramagnetic substance. These paramagnetic substances, they retain magnetic properties, whereas ferromagnetic substance, they do not retain magnetic properties. So you just go through all those discussions so that you will have a thorough idea and a thorough concept about the uses of a solenoid. Keep in mind that a solenoid also acts as an inductor. It stores energy in the form of magnetic field. Thank you.